For literally millennia, we've built our world by hammering, melting, and casting metal. But we are right now on the verge of a completely new era. We're talking about moving from the ancient forge to a technology that can print solid metal layer by tiny microscopic layer. And this is the story of how that whole revolution is happening. And it all starts with a machine, one that a lead researcher on the project called, and I quote, an alien-looking, robust, brutal machine. I mean, just picture it. A 2-ton beast that hums with potential, wielding this powerful laser with just unbelievable precision. So what exactly is this thing doing? And, maybe more importantly, what could this crazy futuristic device possibly have in common with, say, the blacksmiths of the Iron Age? Well, believe it or not, they're both trying to solve the exact same problem. How do you shape metal into useful things? Okay, so to really get how radical this new tech is, we kind of have to look back a little. Forging metal. I mean, that's a craft as old as civilization itself. But the basic rules, the very definition of what it even means to make something, well, that's all being completely reimagined right now.
For thousands of years, our go-to method was pretty simple. Pour molten metal into sand molds.
Yeah, it was crude, but hey, it worked. Then things got a little more sophisticated with something called investment casting, which is a really clever process that uses wax models to get much more detailed shapes. And that was the top-of-the-line tech for centuries. The next huge leap forward didn't come into the 1980s with plastic 3D printing, mostly for prototypes. And then finally, in the 2000s, we figured out how to do it with metal. So here's the really crucial point. It's a fundamental shift in how we think about making things. For centuries, we've done what's called subtractive manufacturing. You start with a big block of metal and you just carve away everything you don't need, like a sculptor. It works, for sure, but man, it can be wasteful. 3D printing, though, that's additive. It builds parts from the ground up, adding only the material that's actually needed, layer by tiny layer. So one of the most popular ways to do this is a process called powder bed fusion. It sounds complicated, but the idea is pretty cool. A machine spreads out this super thin layer of fine metal powder. Then a high-power laser zaps a specific pattern, melting and fusing that powder together. Then, boom, another layer of powder goes down and the laser does its thing again. You just repeat that thousands and thousands of times, and eventually you've got a solid metal object, built from scratch. Okay, so the technology is amazing. But what happens when you try to print one of the most demanding, most difficult metal parts ever conceived? Well, that's where the real challenge begins. I mean, we are talking about a jet engine turbine blade. This little component, it's basically the heart of the engine. It's spinning thousands of times a minute while gases hotter than molten lava are just blasting past it. It is an absolute miracle of engineering, and it pushes materials to their absolute breaking point limit. Now, to survive that kind of punishment, these blades have to be made from something called a superalloy. And honestly, these are materials with what you could call literal superpowers. We're talking about the ability to maintain their strength at temperatures that are nearly 80% of their own melting point. I mean, your average piece of steel, it would just turn to goo under those conditions. So you're probably thinking what I was thinking. Okay, we've got the super strong material, we've got the super advanced printer. Why not just hit print and make an even better turbine blade? Well, that's the puzzle, isn't it? It is just not that simple. See, the problem isn't really the outside shape. It's what's happening inside the metal on a microscopic level. That laser creates intense heat, right? But then the metal cools down super fast. This rapid heating and cooling creates massive internal stress. You can think of it like this. If you try to flash freeze water, you don't get a perfect clear ice cube. You get a cracked, cloudy mess. It's the same idea here. The internal crystal structure, what scientists call the microstructure, it becomes totally unpredictable. The part can literally crack and tear itself apart while it's still being printed. And this gets right to the heart of the problem. You see, most metals are what's called polycrystalline. That just means they're made of tons and tons of tiny little crystals or grains. The problem is the boundaries where these grains meet. Those are weak points. So for something like a turbine blade that's under incredible stress, the holy grail is a single crystal structure, just one continuous, flawless grain with zero weak spots. That is the absolute dream. But what if I told you that dream is now becoming a reality? Yeah, thanks to a breakthrough that could honestly change manufacturing as we know it, forever. Over at the Indian Institute of Science, or ISISC, a team of researchers has been working like crazy on this puzzle. They've been using this combination of intense computer simulations and tons of real-world experiments, and they've cracked the code. And here is the proof. They successfully printed a 100 millimeter tall rod of a nickel-based superalloy as a perfect single crystal. Now, okay, 100 millimeters might not sound huge, but believe me, this is a monumental achievement. It proves that their process is stable and controllable over a pretty significant height, something no one else had ever managed to do with this method. It's basically the hello world moment for printing these perfect materials. It opens the door to creating real, functional parts. And look, this isn't just about jet engines anymore. Mastering this technology unlocks incredible potential across so many industries. I mean, aerospace and defense, that's the obvious one. But think about custom medical implants, high-performance car parts, the list goes on and on. Being able to print complex, super strong metal parts on demand, it is an absolute game changer. Just take a second and imagine this future with me. A future where a custom hip implant is printed to perfectly match your body, with a porous structure that lets your own bone grow right into it. Or a future where entire rockets are printed in just days, not years. Or how about this? A future where a super rare spare part for a classic car can just be downloaded and printed anywhere in the world. It completely changes what it even means to order something. And all of that leaves us with a pretty fascinating question to think about. Once this technology really matures and we can reliably print almost any metal part anywhere in the world on demand, what does that actually mean for our world? What happens to global supply chains, to massive factories, to the very idea of spare parts? You know, the next industrial revolution might not be televised. It's going to be printed.